So, help me out here. Ooh. What's this here?
7, 2.
2. I like it. It can't possibly mean straight up division, because we already have a symbol for division. This has got to be, especially this ugly symbol, it's got to be something different. And I don't know if you guys, so this is 2. So the answer to a log is the power that this base needs. And the relationship between this and a root is that this tells me the power that I want. This is the second root, this is the square root. And it's looking for the base. A logarithm tells me the base I want, and it's looking for the power. So that's the relation. Not the same. They seem kind of related, because they are, but they're not the same thing. So that would be 7. The answer here is 2, and the answer is 7 for the same reason. The reason for both of those is this fact. All right, I like it. So what base is needed if I square something to get 49? 7. What power is needed if I raise 7 to some power to get 49? 2. Maybe. So this fact leads to those 2 answers for those separate things. The big thing there is the symbol. That's what throws people off. They assume it's going to be disgusting because all of a sudden there's a freaking word there. That's got to be gross. No. It's just you got to know what the question is that it's asking. What if I had log base 2 of 16?
4.
Why?
2 times 2.
Yeah. Takes 4 2's to multiply to be 16? Or 2 to the 4th power is 16? I like it. Cool. So the only way it can get difficult is if I give you kind of large numbers, but we already talked about how to attack that. Or if I give you kind of gross fractions or something. We already talked about how to handle that. So for example, if I had log base, what you got, Jeff? 4 of 1 over 64. Good. So you say, I know it's going to be a negative, and then you can forget about that for a second. Because you already took care of the 1 over. And then how many 4's multiply to be 64? 3. And then check it, you go 4 to the negative 3. That would be 1 over 64. Check. 4 to the negative 3 is 1 over 64. I like it. That's what math, a big part of math tries to do, is it tries to capture an idea in a concise way. It's our job to kind of catch up with the language. It's just a different language. What the hell does that mean? Translate it to English. What does it take? How many 4's does it take to multiply 1/64? Negative 3. That's kind of weird, but that negative just means you're going to flip them. I like it. All right, so logs by themselves are not a problem. Let me see. Anything else freaky? Something like this here, just to remind you guys. Log base 117 of 1. 0. Because anything to the 0 power is 1. I like it. So actually I could just write log, become a G. Base B of 1 is 0. Now there are some restrictions on what the base of a log can be. Assuming those are met, that's a true statement. I like it. All right, how we go so far? Okay. Sort of. Let's try to graph a log. That's a phrase you never thought you'd hear.
You're funny.
What happened? Try to graph a log here. So let's say graph y equals log base 3 of x. I want to pick smart things to throw in there. I want to be intelligent in what I throw in there. Who remembers what cannot be true about x? We had this discussion. There was a problem on that sheet yesterday. The answer was undefined. Yeah, it can't be 0. You can't raise something to a power and make it 0. You can raise something to a power and make it as small as you want it to be, but you can't make it 0. So here's what I would do. If I have to graph a logarithm, I would start with fractions. They're the smallest that it could be. So I'd start with stuff. Now, why I wouldn't pick 1/7. That's silly. Since the base is 3, I would pick like 1/9 and 1/3. So what is log base 3 of 1/9? What do you have to do to 3 to make it become 9? And it's going to be negative that. Negative 2. I like it. 3 squared is 9. So 3 to the negative 2 is 1/9. What's log base 3 of 1/3? All I have to do is flip it, so it's going to be negative 1. I don't want it to change, I just want it to flip. So first power would keep it the same, but a negative power would make it flip. So that's negative 1. What's the next smart thing to put in there? Yeah, 3. But the next one would be 1. I can't do 0.
Sorry, yeah, 1.
Yeah, but the thing that would make 0, the answer is 1. What's log base 3 of 1? Well, I just told you, and we just talked about it. 0. I like it. And then log base 3 of 3 is, what power does 3 need to become 3? 1. And then if I wanted to, the next smart thing would be 9. Now, just to make sure you understand, I mean, 2 would have an answer, 5 would have an answer, 7 would have an answer, but they would not be answers that I want to try to graph. I'm just capturing the points. I'm going to fill it in. And of course, when I fill it in, I'm capturing all those freaky-ass answers in the middle. But I'm going to pick points that I can actually graph easily. Sure enough, log base 3 of 9 is 2 because 3 squared is 9. I like it. So the answer to log is always a power. The power that the base needs to become the inside. So now if I'm going to graph this, be a little smart. I don't need much of anything back here. So here's my, let's do 1, 2. Might as well put 3 there. And then we've got, the outputs are going to be between -2 and 2. Got it. So I got 1/9 goes to -2. So 1/9 doesn't really matter. We're just doing it with the hand. It's going to be way down there somewhere. Right? How are we doing? That's a point, right? 1/9, -2. X, Y. X, Y. Are you guys doing all right? We just made an XY table. So then I can graph the points. The points are not the most beautiful thing in the world, but we're just doing this by hand. Doesn't have to be beautiful. 1/3, so that's roughly right there. -1. 1, 0. Plop. 3, 1. Kabam. And then 9 is way over there, but it's not. It's going to get 9 is going to be a 2 finally, so it's going to be rising very slowly. And what's going to happen here is that same thing we saw on the exponential. There's going to be an asymptote here, so it's going to be. So here's the thing, remember, what is this related to? What function is this the opposite of? Kind of a freaky question. We did talk about it a couple times yesterday, but it's all new. Log base 3 asks what power does 3 need to become something. So the opposite would be if I knew the power already. So the opposite function is y equals 3 to the x. That's the opposite. Because what did we say the other day? Log base 3 of 3 to the m. What happens to these things? Why? Because they are freaking opposites. I love it. So what's the opposite function to this? This one. They're the opposite functions, because that's what we talked about yesterday. But go with me. This is where things get kind of neat. So Jackie, what you remember is, if I have this function, it's got to be asymptotic. It's going to look like this, right? 3 to the 0 is 1. 3 to the first power is 3. 3 to the negative 1 is 1/3. How would you say those functions are related?
But opposites of each other.
But graphically, visually. There's symmetry there. You guys see? There's symmetry. Where's the line? Where's the mirror that somebody put down? Where's that mirror at? Yeah. Go ahead. Draw it in the air for me. Where's the mirror?
It's right here.
Yeah, it's right here. Y equals x. Every function's opposite will have this symmetry around this line. So if I graph the cube root of x, it would have this. It would be symmetric to x cubed through this line. It would be like a mirror sitting right here. That is kind of cool. That is something we don't have the most time to get into. It's too bad for me. I'll let it go. But hopefully you guys see that visually these two should have a really clear relationship, because they have a clear relationship algebraically. They kill each other. They cancel each other out. So sure enough, if I put a 1 in for the blue guy, I get a 3 out. If I put a 3 in for the purple guy, I get a 1 out. They undo each other. One makes 1 go to 3, the other one makes 3 go back to 1. They undo each other. So they really just switch their points. Okay. So all I need you to, from all that discussion we just had, is, can you make an XY table and plot it over, right? So what do exponentials look like? What does a to the x look like? It looks like this. Wee-haw. And what does log base something x look like? It looks like wee-haw. Rough. Cool. I like it. So it's more important to know the general form of a function, because then you can fill the details in with an XY table. Okay? So, the next kind of level of this, now that we know what logs are, I need to know how they act. I need to know, what if I add two logs together? What if I raise it to a power? What happens? Okay. So I do have a bit of a handout for this. It's going to have what I'm going to talk about listed out for you. But I want to first throw it at you. So remind me, the answer to a log is always going to be a what? A power. Good. A logarithm always the answer for it is always going to be a power. So all the rules of logarithms, all the properties of logs are the exact same as the properties of powers, because logs are powers. Really want to. Right? Log base 3 of 9 was 2, because the log is the power that the 3 need. Logs are powers. So what do I do when I multiply two things with like bases? I would do what with their powers? When I multiply, so recall. X squared times x to the 5th.
Yeah, 7.
X to the 7th, I love it. Right? X to the 2 plus 5, maybe, really. And watch how that translates into logarithmic form. A log is a power. So if I have a base of b, and I multiply two things together, it's going to be a little bit weird, but I want you to really see how the power, the rule comes out. I'm going to add this guy's power to this guy's power.
Okay.
Now, I was debating with myself about whether or not to show you the proof of this. Sure. Let's see how that goes. And then I'll show you the proof, and then I'll try to step it back and just show you what to focus on to make it make sense. Let's see. So let's say, let me try to relate it to what I've got over there. So let's say log base b of x is a, and log base b of y is, that's kind of sucky, but oh well, c. I'm going to go with it, just go with it. Why can I say that? Because I don't know what they are. So I can call them whatever I want you to work with it. This is a proof, so if you don't quite get everything here, it's not the end of the world. Yes. Okay. So help me out. Just as a side note here, what would this look like in the other form? How can I rewrite this? We keep doing this. Let me see if you guys pick up on this. I can write this as b to the a equals, so x is b to the a, and y is b to the c.
Okay.
Cool? All right. So then what's xy?
What we wrote over there.
Both of them combined.
What's xy right here?
B,
B to the a times b to the c, which is b to the
A, C.
a plus c. Be careful now. You add powers when you multiply like bases, right?
So you write them like that, like plus.
Yep.
Like that? Okay.
So then what's log base b of xy? It's going to be log base b of b to the a plus c. All right, let me stop there for a second.
You cancel.
I love you guys. Do you see what I did? Is everybody cool with this? This is true, period, because of what I wrote here. This is true because of what I wrote here. Why did I look at x times y? Because that's involved there, right? So then I just took these and multiplied them together, and that's this. All right. So everybody cool with that step right there. So if I write that, that means that x must be this. If I write that, that means y must be this. So xy must be that. Now I'm going to take log base b of both sides. Right? So then I get log base b of xy equals, what is log base b of b to the a plus c? We had a silly problem like that. Remember log base b of b to the eighth? Remember that problem? Yeah, it was just 8. So this log base b of b to the a plus c is a plus c. What power does b need on it to become this? Well, it needs freaking that power. But what was a? Yeah, you do. A was log base b of x.
Yeah.
And what was c?
Oh, I think I remember.
C was log base b of y. Come on.
That's what you write? To answer all of that?
This is the proof of that statement over there.
Oh, cool.
Because again, what do logs do? Logs focus on the power. So this log says the power of this product, the power on the resulting product is going to be the sum of the powers that were on the original. That's what we see right here. The answer, what power did it have? The sum of the original powers. That's the answer it had. That's all that statement says. So a logarithm, when I take a logarithm, it's focusing on the power. That's why the properties of logs are going to be the same exact properties of powers. What do I do when I multiply things that have the same base? I add the powers. So what do you think this is going to be? What do you do when you have the same base and you divide? What do I do with the powers? So again, what's x to the fourth divided by x to the first?
You subtract?
Oh.
Subtract, yeah. So it's going to be log the power on the x, or the power that gets the x, minus the power that gets the y. So it's just to remind you, this was the proof. I was debating whether or not I was even going to show this to you, and I did. So if you don't totally get this, not the worst thing in the world, but this is why this is true. Now here, you just, when I multiply things with the same base, I add the powers. I mean, that's how you remember that rule. When I divide things with the same base, I subtract powers. See, that the base is b, isn't it? So they have the same base.
Here's my concern. Are they going to be? I know you're going to start putting numbers with that, right?
Yeah, of course.
Okay.
So I'm going to follow this up with an example of a nice concrete example. That's always nice.
That's not, that was it.
No, sir. No.
I was afraid that was
This is the rule, and what are you going to have to do? Apply it. Oh shit. That's how math always works. And then this last rule is actually the most important rule. And it's really just this dude repeated. So let me build up to this last rule. What do you think about this here? Log base b of x times x. Just use that same rule, what do you end up with? Equals log base b of x plus log base b of x. And what's log bx plus log bx? No, careful. I'm adding. What is m plus m? M plus m is 2m. What is one of these plus another one of these? 2 of these. You with me? And of course, what's x times x really? X times x is x squared. I like it. Now watch this. What's log base b of x cubed? Well, that's log base b of x times x times x. That's log base b of x plus log base b of x plus log base b of x. And of course, how many log base b of x's do I have now? 3. So what about log base b of x to the 111th power? Well, that would be shit. What's going to happen? What pattern can I pick up on? How many of these am I going to list? 111 of them, because I'm going to have x times x 111 times. So it's just going to end up being 111 times log base b of x. So what's the rule then? The rule there, what keeps happening? Whatever that power was, this power. So what's the rule I can write? What's the rule I can write? What if I would have put an 18th power there? What would have changed in the result? There would have been an 18 there, right? So what's the rule? Log base, get in there, b of x to the m equals m log base b x. So that just comes down. And this is still a rule. What do I do when I raise something to a power to another power? What do I do with the powers? No. I multiply them. Yes. So see, look here. This is a power here. Logs are powers. And this is a power, isn't it? So when I raise a base that has something to a power to another power, I multiply the powers. That's still a property of logs. Every property of log is a property of powers.
Okay.
All right, now let's do some concrete examples. What's log base 7 of what you got, Jeff? 2. You can do it, man. Well, let's do this. What's log base 7 of 14 minus log base 7 of 2? Can you do log base 7 of 14? You'd have to figure out what? To be able to do this by itself, you'd have to figure out what exactly. What does log base 7 of 14 need? No. What question is this asking you by itself? What does mu need to become mu?
How many sevens does it take to become 14?
Say again?
How many sevens does it take to become
Yes.
14?
How many 7s does it take to multiply together to be 14? Not 2, because 7 times 7 is 49. Right? So the answer ain't 2. In fact, the answer ain't nothing I can figure out. You guys understand? 7 times 7, how many times is 14? There is an answer. It's going to be some fractional answer. Maybe you guys can see. Right? Well, it's going to be like 1 point something. It's a little more than 1 7, but a lot less than 2 7s. And then what about this one? Oh shit, I can't even begin to imagine. It's going to be less than 1 something. But what property can I use? You guys see how this is actually going to be the reverse. What property can I use?
What do I?
Which involves subtracting.
Okay.
Yeah, when I have log with the same base subtracting things, I can rewrite it as,
14 over 2.
yes, it'll be log base 7 of 14 over 2. I was subtracting power, so I must have been dividing things.
So that's 1.
Log base 7 of
7.
7, which is
1.
1.
So if it has the same base, you could.
Yes, good, I like it. That's the key. If that was 7 and that was 6, I'm screwed.
Dang.
Yes, sir.
So say, because we do, in my calculator at least, there is just a normal, just log one, but how do you put like log and then you do the thing? You know what I mean?
Too bad.
Is there really no function for that in a calculator? Or
I won't
or
say.
you just won't tell me?
I won't tell you. If you put some effort in, you might be able to find it, but
YouTube's sick.
even then, it's too bad. I still need to see
I
some
think
kind of
Google.
reasoning. Yeah.
So, I'm pretty sure we've already done it or not. Never mind. The problem's like if you do this, but like you just said, the bases are the same, so the bases aren't the same. Are you going to do a problem like that, or?
Well, that would be a little bit evil. I probably wouldn't do it, but I mean, the whole thing rides on the fact that the bases are the same. I mean, when do I subtract powers? When I divide like bases, right? So to screw this up, if I had x to the 4th over y, can't do shit. So if I had log base b of 7 minus log base a of 2, I can't do anything. I don't know what the shit that is. But if I made the bases the same, then I can consolidate it with the property. I like that. That's why the property is so nice, because it requires such a stringent thing. They must have the same base or else this can't be used. All right, let me see. Let me do this. Let me give you this handout. So this side is what we just discussed. This side you might not want to look at yet. You can if you want to. I want you to work out the problems that are on this side with the red writing.